Welcome to the 2016 BC free response questions. All right, we're going to start with question number 2, which is calculator active. I guess I should turn on my calculator here. Sorry about that. All right. Okay, so let's take a look at this problem. This particular problem, we're looking at a graph analysis problem here. So at time t, the position of a particle moving in the xy plane is given by this parametric equation. And then we're also told the derivative of x with respect to t. The graph of y, consisting of 3 line segments, is shown. And then we also know that at time 0, we have a position for the particle. So we want to start by finding the position of the particle at time 3. When you are doing position problems with parametrics, you almost always are going to be using the accumulation formula. So x of time 3 could be found by doing x at time 0 plus the definite integral from 0 to 3 of x prime. And we'll do this with respect to t. And I'll use the calculator that for this, x of 0 is 5. And then again, I'll just use the calculator from here. Now I have not yet defined x of t, so I'm going to do that. I'm going to call that f of t. Just for me, that helps me remember that that is not the position, but that this is a velocity function. We'll see if that works, if I can remember that properly. So this will be t squared plus the sine of 3t squared, as I define that. And I'm just going to double check that really quickly before I move on, which I think is good practice. And then I'll do the, let me start by doing 5 plus, because I do want that initial condition of 5. So 5 plus from 0 to 3, because that's my time change. And then I want of the rate of change of x, which I called f. And when I do that, it looks like I get 14.377. You could take extra decimal places if you wanted. All right, if I want to then find what y of 3 is, well, this one, I could actually look at the graph because they actually have the graph of y given to us. So y of 3 is right here. Now, where is that exactly? You might look at it and go, it looks like -1/2, and you'd actually be correct. But you really probably want to know that for a reason. So here's the reason. If we look at the slope of this segment, it's up 1 and over 2. Well, proportionally, if we only wanted to move over 1 instead of over 2, that'd be up 1/2 and to the right 2. So from a height of -1 up 1/2, yep, this is a height of -1/2. And I got that from the graph. You don't have to explain where it came from, but that's where I got it from. So for part A, the final answer here would be 14.377, -1/2. I did not have to use accumulation for the y-coordinate because they gave me a graph of y. All right, part B. I want to find the slope of the tangent line. Slope of a tangent line always means dy over dx. Well, we don't have that because we have everything in terms of t, not x. So we need dy over dt divided by dx over dt. And we want this specifically at t is equal to 3. So we're going to want to evaluate this at t is equal to 3. So dx over dt, I've got that expression right here. So that'd be 3 squared plus the sine of 3 times 3 squared. And I'll use a calculator for that. But on the numerator, or I could just write, if I wanted, maybe it'd be a little less risky. If I just said dx of dt at t equals 3, that'd be fine. And then for the numerator, dy of dt, we don't have an expression for y. Therefore, we don't have expression for dy. But what this would be is this would be the slope at 3. So this is looking for the rate of change of y. So this is the slope at t equals 3 of this graph, which this graph we just said had a rise of 1 and a run of 2. So this would be +1/2. And I'll use the calculator to finish this. So I'm going to be doing 1/2 or 0.5 divided by the rate of change of x, which I called f, specifically evaluated at 3. And I'll let the calculator do that work for me, and I'll get 0.050. Now, I want to take a little point here about the scoring guideline. The scoring guideline, 0.0, I messed up, 0.0502. Now, if you rounded, you would have that. Same thing if you truncated. The scoring guideline says this. What I'll tell you is this is 5 years old. They no longer like that. You really should keep that third decimal place there because it doesn't truly terminate after the 5 for that decimal. So please make sure that digit's there. You could put in additional digits if you felt so inclined. Okay, but make sure that third digit of 0 is still there for any decimal that doesn't actually terminate. All right, part C, we want the speed of the particle at t equals 3. Well, speed, our formula for speed for a parametric is dx over dt, quantity squared, plus dy over dt, quantity squared. And this specifically needs to happen when t is equal to 3. Well, keep in mind that we actually already have some of this because we already know what dy over dt is at 3. So really we could think of this as dx over dt, quantity squared, plus 1/2 quantity squared when t is equal to 3. All right, I'm going to jump to the calculator. So this would be the square root. And you might remember I called dx over dt f of t, but I want this specifically evaluated at 3. Now I'm not doing derivative at a point here because f is already the derivative. Plus, the slope of y was 1/2. That counts as our dy over dt, and I would like that also to be squared. And I'm going to convert that to a decimal to get approximately 9.969, 9.968. You can write that how you want. But correctly. You can choose to truncate or round. I'll truncate. Doesn't matter. All right, part D, find the total distance traveled. Now remember, if we are moving only in one direction, total distance is the definite integral of the absolute value of the velocity. However, if we are doing a parametric total distance, we need to read that as arc length. So we want to do the arc length from 0 to 2 of basically essentially the speed. dx over dt, quantity squared. By the way, they give you a point just for recognizing that this is asking for arc length, even if you struggle in doing the problem. Now, one of the tricky things about this one is the dy over dt. Because dx over dt, we have a function for it, and the function's true for the entire interval. But dy over dt, remember, is our slope of y. We want to go from 1 to 2. We have one slope from 0 to 1, or from 0 to 2, pardon me, and a different slope from 1 to 2. So I'm going to need to split this into two different integrals because I have two different slopes. Going from 0 to 1, the slope of this segment, which would be my dy over dt, is down 2 over 1, versus my slope for the horizontal segment is 0. So I'm going to need to split this. My first integral would be from 0 to 1 of the square root of dx over dt, quantity squared, plus -2. I would put that negative there. I would not write that as a 4. I think it would be beneficial for the reader to know what you're using there. Plus the definite integral from 1 to 2 of the square root of dx over dt, quantity squared, plus a slope of 0 squared. And again, I would still write that because it is actually important for the reader to be able to see this. Now we can input this all at once. So I'll do the definite integral from 0 to 1 of the square root of, remember, I want to square the rate of change of x, which I called f. And I do want to square that. Plus the rate of change of y on that interval, which is -2, quantity squared. Now you could certainly write that as 4 dt. And then I'm going to add on to this, I usually arrow over once more to get that cursor nice and big, another definite integral. This one going from 1 to 2. And then of the square root of the rate of change of x, which I'm calling f of t, quantity squared, and then I won't put in plus 0 squared for the rate of change of y. I did write that for the reader, but now I'm doing this for myself. I'm going to get 4.34987. However you decide you want to round that is up to you, as long as you at least, at a bare minimum, correctly round to 3 decimal places or truncate. I'll just truncate. All right, question number 5. Question number 5. The inside of a funnel of height 10 inches has circular cross sections. So the whole funnel has a height of 10 here, as shown in the figure above. Now, at height h, so height can change, the radius is given by this expression. So our radius is changing for heights that go from 0 to 10, which would be the top of the funnel, all the way down to the bottom. R and H are measured in inches. First, we want to find the average value of the radius. Notice this says average value and not average rate of change. Average value is 1 over b minus a, and we're going from 0 to 10, of the definite integral from a to b of the original function r. Now, this one is not calculator active, and it did say to actually find it. So I'm going to need to actually work on finding this. So I'm going to rewrite this as 1/10 of the definite integral from 0 to 10. I'm going to distribute this. This would be 3/20 plus 1/20 h squared. And this is dh. Now, if you wanted, you could take the 1/20 and put it out front with the 1/10. Maybe that would have actually been a little bit wiser, but that's not how I thought of doing it just now. So this would be 1/10, and I'm going to integrate this. This would be 3/20 t plus, let's see, I'll raise my power and divide by that new power. And I want to evaluate this at 10 and 0. So this would be 1/10 times, if I plug in a 10, 30 over 20. You could choose to reduce that or not. Plus, let's see, that'd be 1,000 over 60. I'm not going to simplify it, so whatever. And then minus 0, which you actually don't have to write. And I would leave it like that. I would not compute that further. I would just leave it like that, personally. I think in the scoring guidelines, they did simplify that for us, so you could look at that. I didn't write it down to see what that would be. All right, part B. We want to find the volume of the funnel. Not fennel. Now, sometimes people look at this and they see a cone. This is not a cone. Cone would look like this. This is not a cone. They gave us a hint what this is. They said we have circular cross sections. This, here's like our axis right here. This is a revolution. We want to view this as a revolution. This is revolving around a whole bunch of circles, and we want to accumulate all the circles. This circle and this circle, and we want to accumulate all of these. So we want to do the volume of a rotation pattern here. So the volume could be found by doing pi times the radius squared. And our radius is r of h. Now the interval here for the radius, h is our interval, is from 0 to 10. So I'm going to start, because we do actually have to not just write an expression, we have to find it. I'm going to go ahead and start by simplifying this. Now what I did is I squared the 1/20, and I did decide to take that out front as 1 over 400. You could write that as 1/20 quantity squared if you wanted. And then you should expand out the 3 plus h squared. Make sure you don't square any individual terms. This is a binomial times a binomial. So this would be 9 plus 6h squared plus h to the 4th once you expand that. Now I'm going to go ahead and use the power rule. So I'd have pi over 400 times 9h plus, let's see, that'd be h to the 3rd. And if I divide, that'd be 2h to the 3rd plus 1/5 h to the 5th, pardon me. And then I'm going to evaluate this at 10 and 0. You do actually need to write the evaluation. You do not have to compute the evaluation, but you need to write it. So this would be 9 times 10, or 90. You don't have to compute this. You could just write 2 times 10 to the 3rd. 10 to the 3rd is 1,000 times 2. That's easy enough. For that one, I'm not going to do this one. I'll just do 1/5 times 10 to the 5th. I just don't want to write all those zeros. And then all of that minus 0. And I would leave it like that. Oops, I almost wrote this wrong. This is pi and 400. Not sure how it magically changed. Glad that eventually I saw that before I moved on. Part C. The funnel contains liquid that's draining from the bottom. Now, as the liquid drains from the bottom, what basically is happening here is that this height is going to go down. So the height is changing. It's not always going to be staying the same height. At the instant when the height of the liquid is 3, the radius of the surface is decreasing. So dr over dh, remember h is my input variable here, at a rate of 1.5 inches per second. It's decreasing. So it is a negative rate. We do have to interpret that as a negative rate. At this instance, what is the rate of change of the height of the liquid with respect to time? So we want to find the rate of change of the height, but with respect to time, not with respect to height. So that's interesting. So I'm going to start with my formula for radius. Now, again, I would rather have that distributed. For me, that's easier for me to process. I don't know if you want, you can just keep that a multiplier out front if you prefer. Some people do it that way. I want to do the rate of change of this with respect to time. Well, right now, I'm going to just take this derivative of all of this. None of these are t. So I'm going to do all of these implicitly. So this would be dr over dt. Oh, wait, I'm going to go back really quickly and see how they named this. Per second. Ooh, I did this wrong. The radius of the surface is decreasing at a rate of 1.5 inches per second. This is actually dt. Okay, that's good news. All right, so I have dr over dt, derivative of a constant will zero out. And then this would be 2 over 20, or 1/10, h times dh over dt. Make sure you're doing this implicitly with respect to time. That's h. Doing great. All right, well, dr over dt is negative 1/5 equals 1/10 times the height of 3 times dh over dt. So I will need to multiply by 10 and divide by 3, and you could leave it like that if you wanted to. I'm wondering if units might be important. They often are in word problems, so I am going to put in the units. But if you wanted to reduce this, you could. This would be negative 2/3. Now, they said this is the rate of change of height. Height's in inches, and it's with respect to time, and time they've mentioned is in seconds. So there's number 5. Last one is number 6. The function f has a Taylor series about x equals 1 that converges to f for all values of x in its interval of convergence. And then we have a couple things. We know the value of f at 1, the first derivative, and then we have a formula to find any additional derivatives. We want to write the first 4 non-zero terms and also the general term for this Taylor series. So since I'm writing the first 4 terms, I'm going to need a couple more derivatives. So I'm going to need to know what the second derivative is. So the second derivative at 1, I'll be replacing n with 2. Negative 1 squared would become a positive. 2 minus 1 would be 1 factorial. So the numerator's a 1. And on the denominator, I have 2 squared. You could write that as 2 squared or 4. It's up to you. I'm also going to want 4 terms that aren't 0. So I'm going to continue looking. I'll look at my third derivative, evaluated at 1. So now I'm substituting n is a 3. So since negative 1 is to an odd power, that'll be negative 1 times 3 minus 1 is 2. Factorial is still just 2 over 2 to the power of 3, which is 8. So this is negative 2/8 or negative 1/4 if you prefer reducing, totally up to you. Now, sometimes it is actually helpful to keep that as a power. Here on the denominator, I like to keep this 2 squared or to keep this 2 to the third. The reason I'm mentioning that is since we have to write the general terms, sometimes it's easier to see patterns when you have those written as powers, but it's not required. It's up to you. All right, so my Taylor series would be 1. Let's see, minus 1/2. This is centered at 1. So minus 1/2 times x minus 1. And then this would be, let's see, plus, I'm now on this second derivative, 1/4 or 1 over 2 squared if you prefer, times x minus 1 quantity squared over 2 factorial. Okay, that's going to get multiplied there on the denominator. And then minus 2 over 2 to the third times x minus 1 cubed. And then also on the denominator is a 3 factorial. So that's how I wrote it. I don't know if you like it that way or not. And then so for my general term, one thing I can see is that the signs are alternating. The signs here are alternating. So if I start here with like my 0 derivative, I had a positive and then I had a negative. So I'm going to call this n because on all of, like, when I plug in a 0, that'd give me that positive. If I plug in n as 1, that gives me the negative. And then I have x minus 1 to the power of n if I start it at 0. If you choose to start it at 1, you're going to have a slightly different expression, and the reader will take a look at that. Now this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. This down here would be 2 to the power of 0. So this is 2 to the power of n, and then times n factorial, which we're used to seeing on our Taylor polynomials. So there's part A. Part B, write the Taylor series, the Taylor series about x minus, or x equals 1, has a radius of convergence of 2. We want to find its interval of convergence and show our work. Well, if it's centered at 1, then the absolute value of x minus 1 is less than 2. So x minus 1 will be less than 2 or negative 2. And x would be between negative 3 and, maybe negative 1 and 3. This is my start of my interval. Now what I have to do is I have to test the endpoints. So let's see what's happening at x equals negative 1. Now we're specifically looking at the Taylor series for this. I know we have this formula here and you might be tempted to test that, but that's our derivative. That's not the actual series. What I'm going to do is take my series from part A and I'm going to substitute in a negative 1 and rewrite what this series would be. If I substitute in a negative 1, I'd have 1. And then this would be negative 2 times the negative divided by 2, which is another 1. Plugging in a negative 1 in, I have negative 2 squared, which is 4, which will cancel with this 4. So I have 1 over 2 factorial, or 1 over 2. Plugging in a negative 1, I'll have negative 2 cubed, which is negative 8, times this negative will be positive 8, which will cancel out with this 8 on the denominator. And I have 2 over 3 factorial, or 2/6, which is 1/3. And I could continue doing that, but here's how that looks. Now what this really is this part here is the harmonic series. This is 1 over n. So what I've got here is I've got 1 over the infinite series as n goes from 1 to infinity of 1 over n. Now this part of it is the harmonic series. So this is 1 plus the harmonic series. The harmonic series diverges to infinity. Well, when you add 1 to something that's growing without bound to infinity, that also is going to still diverge. So my infinite series then here would also diverge. When you're growing without bound, adding 1, you continue to diverge. So at negative 1, I will be keeping an open interval there. I'll now check and see what's happening when x is equal to 3. And like I did before, I'm going to go back to the series I wrote in part A, and I'm going to be plugging in a 3 for x. When I plug in a 3 for x, I get 1. And then if I plug in a 3 here, I'll have 2 times the negative 1/2, which would be negative 1. And then if I plug in a 3 for the third term, I'll get 2 squared, which is 4, which will divide out with this 4, and I have 1 over 2 factorial, or 1/2. If I plug in a 3 in this next one, I get 2 cubed, which is 8, which will cancel with the 8 down here. Now this minus is still here, so I have negative 2 over 6, or negative 1/3. Notice this one's alternating. And so forth. The next term would be positive 1/4, and so forth. Well, what this is this is 1 plus an alternating harmonic series, where I'm going to have 1 over n, but I'm going to have it alternating in signs. I'm going to start this with n equals 1 because it makes it a lot easier for those denominators. N equals 0 didn't make sense for that first term, so I just kind of started these at 1 and added that in. Well, let's take a look at the alternating harmonic series. The alternating harmonic series, it is alternating. The terms are decreasing in magnitude. and also the limit as n approaches infinity of the non-alternating part of this 1 over n is equal to 0. So this converges. This has an actual sum. If that part converges, if something converges and has a sum and you add 1 to it, well, 1 plus a finite number is going to be just some other finite number. You don't really have to explain that. The reader is going to understand what you're saying there. So at 3, we will have a closed interval. There's our interval of convergence for part B. Part C. The Taylor series about x equals 1 that we found in part A can be used to represent 1.2 as an alternate f of 1.2 as an alternating series. Use the first 3 terms to approximate f of 1.2. This part, I'm just going to go to my series. I'm going to use terms 1, 2, and 3 and substitute in 1.2. So this will be 1 minus 1/2 of 1.2 minus 1 plus 1 over 2 squared. You could write that as 4 if you feel like it. Times 1.2 minus 1 squared over 2 factorial. Don't need to simplify that. I would not bother. There's my approximation. This is approximately f of 1.2. Part D, we want to show that this approximation is within 0.001 of the exact value. In other words, we want to look at the error of this approximation. Now, they gave us a hint. They told us in part C that this is going to be an alternating series. So we're going to use the alternating series error bound, which basically just says the error, the absolute value of the error, which is what they're talking about here, is less than or equal to the absolute value of the next term. Specifically, the next term after my approximation, but I do want to evaluate this where x is 1.2. So my error will be less than or equal to, well, the next term, I can see from what they had me write in part A, the absolute value of negative 2 times 1.2 minus 1 cubed over 2 to the third times 3 factorial. And I would want to be able to show that this is less than 1 over 1,000. They actually don't make you simplify this, so you could just leave it like that and just trust that it really is. But if you wanted to verify it and you had the time, you could think of this as negative 2 times 1.2 minus 1 is 0.2, or 2/10, which would be raised to the third power, and then divided by 2 to the third times 3 factorial. So this would be negative 2. And then what I would think of this is 2 to the third on the numerator. And we have a 2 to the third on the denominator. And this 10 to the third would also be on the denominator times 3 factorial. So those are going to cancel out. So I have negative 2 over 10 to the third is 1,000 times 6. So this is negative 1 over 3,000. Oh, absolute value. And yep, 1 over 3,000 is indeed smaller than 1 over 1,000. Not that you really needed to do that. This all here is just gravy, and maybe you would not risk it. But if you were feeling like, I'm not really sure if I got it right or not, and you wanted to check, this right here maybe be optional, and I probably shouldn't have boxed it because I really want them to understand that my final answer is right here. This is my final answer. If you box something, they will understand it's your final answer. And that is it for the FRQs for 2016 BC only.